In our notes for today, we are reviewing and adding to our knowledge about how to solve equations. So there's some things we expect you to come in knowing how to do. You should know how to use inverse operations in order to solve an equation. You should be able to deal with variables on one or both sides, and you should be able to distribute when there's parentheses like is shown here, and you should be able to collect like terms. So before you move forward, I'd like you to pause and try to solve this equation and be really honest with yourself about whether you're able to do all the steps necessary to solve it. This doesn't have anything new, and it should be all things you're able to do coming in. So you should come up with x equals 41 over 9. If you're not able to come up with that answer, then I need you to go back to the review videos. There's a series of 3 review videos that talk about what you should already know before coming into Algebra 1 about solving equations. So if you are confused and don't know how to work your way through this problem, then go back to those review videos, because in this one I'm just going to focus on what's new for Algebra 1 and not going over all of the old stuff. So the new things, so we talked about there's solving with two-step equations, solving with variables on both sides, distributing, collecting like terms. That's all the review stuff. I'm going to start here in our notes with what's new, which is using cross multiplication. Cross multiplication is kind of a shortcut for just regular multiplying on both sides like we do with inverse operations. So as an example, if I had x over 4 is equal to 6, then our inverse operations tell us that we would multiply both sides by 4. The reason for that is my operation that's happening here is division. I'm dividing by 4. And in order to undo division, we multiply by 4 on both sides of the equation, and that cancels out the divide by 4 operation, and we're left with x is equal to 24. So hopefully we got that down. So we multiply to cancel division. But what you haven't seen before is dividing on both sides. So in this problem, we're dividing on the left side by k plus 3 and dividing on the right side by k minus 7. In order to get rid of either of those denominators, since those are division operations, we need to multiply both sides by that denominator. So in order to cancel out k plus 3 on bottom, we need to multiply by k plus 3 on top on both sides. That's going to cancel out this denominator. And on the right side now, I have 5 parentheses k plus 3, which is where we need to make sure we know how to distribute, because that's a distribution operation. Then we need to get rid of the other denominator, so we would multiply both sides by k minus 7 in order to get rid of the other denominator, because that would cancel out this one. So what we're left with on the left is 6 times k minus 7, which we would write like this. And on the right, we're left with 5 times k plus 3, which we write like this. Now it looks a lot more approachable. We can distribute and solve to get our answer. So we would distribute 6 on the left to both of these terms in parentheses and get 6x minus 42. And on the right, we get 5 times k is 5k plus 5 times 3 is 15. Then we would use our inverse operations and say minus 5k and plus 42, so that we isolate the x, and we're left with k is equal to 15 plus 42, which is 57. So this step at the beginning looks a little confusing when we write out all of that multiplication. All we're doing is inverse operations like you're used to doing, but it looks confusing when we write all that out. So what we do is we use a kind of visual shortcut called cross multiplying to stand in for those 2 steps. So we're still doing the same thing. We're multiplying both sides by both denominators, but rather than writing it out in parentheses like I did here and making a whole bunch of stuff written out, we're going to use a visual simplification and say we're multiplying this over to here, And that's what happened with the blue part here, right? It canceled k plus 3 from the left, so the 2 went away, and it showed up over on the right side at the top. Likewise, the 9 is going to show up on the top over here. So we draw these arrows, and on the left now, I have this 9 times this n plus 7, so I get 9 times n plus 7. And on the right, I have 2 times n minus 6. It's the exact same thing we did on the left problem, but a little simpler visual, like from a visual approach. So it's easier to see what's going on, it's less cluttered, and it's a nice like visual shortcut. But it's not anything magical or special. We're literally just multiplying both sides by 2 and multiplying both sides by 9, and then we distribute and solve like we did on the other one. So we get 9n plus 63 equals 2n minus 12. Then we get our like terms together across the equal sign. So this is minus 2n. So we're bringing all the n's over to this side, meaning we take away the constants from that side. And we rewrite it as, on the left we have 7n. And on the right, we have negative 12 minus 63, so two negatives make a bigger negative when we add them. Like if you owe $12 and then you owe 63 more dollars, now you owe $75. Then since we want to know what n is, not 7n, we're going to divide by 7 to cancel out that multiplication operation, and we're left with n equals negative 75 over 7. So cross-multiplying is just a kind of visual shortcut if you have denominators on both sides. Rather than doing the full written out multiplication like I did on the left, we just use these arrows, like we did on the right side here, to simplify and show how we're multiplying on each side. Now, when you write those, notice I didn't put n plus 7 times 9. We're always going to want to put we call this a monomial, a single term, before this one that has a plus. We call that a binomial. So it looks really strange to write n plus 7 parentheses 9. And then if I drew distribution arrows, they'd be going like backwards, which looks super weird. So anytime you multiply a thing with a plus by a thing without a plus, you put the thing without the plus first, and then you put 9 parentheses. N plus 7, that looks normal, and that's the way we want to write that so that distribution looks like we're used to. So that's cross-multiplying. It's nothing really special, but it is kind of new to see denominators on both sides and have to deal with that. Keep in mind that this has to be an equation, and it has to be across an equal sign. So the most common mistake made with cross-multiplying is trying to use it on the same side of the equation. So if you had something like 3/4, that's a bad 4, 3/4 minus 3/2 is equal to 4x. What students sometimes try to do is cross-multiply this thing over here, which is not a thing we can do. The whole idea of cross-multiplying is it has to go across the equal sign. That's the cross part. If it doesn't cross the equal sign, then all you're doing is collecting like terms, and you need to have a common denominator to do that. We talked about that in the review videos. So here, to simplify the left side, we would write this as 3/4 minus, I hate the 4s today, 3/4 minus 6/4 is equal to 4x. So we make a common denominator by raising this 2 up to a 4. And then we combine these, just like collecting like terms, by squishing them together, and we get negative 3/4 is equal to 4x. So don't try to use cross-multiplying on one side of an equation. It has to go across the equal sign, and there has to be only one thing on each side. So if I had, let's just use the example we had in the problem we just did, n plus 7 over 2 minus 3 is equal to n minus 6 over 9. You wouldn't be able to use cross-multiplication here as it's currently written because of this minus sign on the left side. There's not just one term or one fraction on each side. In order to solve this, you would first need to collect your like terms on the left side. So we would need to put this one and this one together before being able to cross multiply. To do that, we would do n plus 7 over 2 minus, and just like we did in this example, we would convert this 3 into a number of halves as well and make it 6 halves and put that equal to n minus 6 over 9. Then we would combine these like terms. They're both over 2. So this is the same as n plus 7 minus 6 over 2 equals n minus 6 over 9, which is then just n plus 1 over 2 equals n minus 6 over 9. Now we would be able to cross multiply. So we'd multiply both sides by 2, multiply both sides by 9, and get 9 times n plus 1 is equal to 2 times n minus 6, and then finish solving it from there, just like we did before. So cross-multiplying is a nice shortcut to use so that you don't have to write out all the multiplication steps on both sides and make your paper all messy. It looks a lot cleaner, but I do want you to understand that underneath it, it's just like a visual representation that we're multiplying both sides. It's still just a normal inverse operation. The second new thing that we're doing this year with equations is called special cases. So you've always seen special cases. You've always seen equations where you end up with x equals a number. So like x equals 2 or x equals 3.7, but x is something. There's a value of x that makes the equation true. In algebra, we're going to have to start considering cases where there may not just be one solution to a problem. So let's look at our first example here. We have 8x plus 5, and then on the right, we need to distribute. So we're not changing the left, but on the right, we're going to distribute and get 8x minus 40. When I try to solve this, I do minus 8x to get all my x's together. And then I would do minus 5 so that all my constants are on the same side. And I end up with 0 is equal to 8x minus 8x is 0, 5 minus 5 is 0. And then on the right, I canceled out these, and I have negative 45. So I'm left with no x's in the problem. So a note you probably want to make here is that special cases happen when all variables cancel. So in this case, all of our x's went away, and we're left with an equation that says 0 is equal to negative 45. Hopefully, we know that that's not true. 0 is not equal to negative 45. This is a false statement. What that means is, no matter what value I pick for x, this equation that we started with here can never be true. There's no value of x that makes the left side equal to the right side. So we know that because we tried to solve it, all the x's went away. So this is the key step where there's all the x's cancel, and then we're left with a false statement. Instead of putting x equals something here, we won't write our answer that way. We actually have to write this answer in words. I know, it's shocking. So we're going to write no solution. So that means that there is no possible value of x that solves this equation or makes it true. So we put no solution as our answer anytime that we end up with a false statement where a constant equals another constant that's different. On the right side, we have 10x minus 6 is equal to, let's just go ahead and distribute this. We get 10x minus 6. So hopefully you can already see that those are the same, but if not, we try to solve it. Plus 6, and we see that on the left, everything canceled. We're left with 0, and on the right, everything canceled. We're left with 0. So this says 0 is equal to 0. Again, all of our x's canceled out, so all of the variables are gone, but this time we're left with a true statement. 0 does equal 0. Or here, even if you didn't do that first step, 10x minus 6 does equal 10x minus 6, no matter what. So in this case, it doesn't matter what x is. If x is 1 or 2 or 7.3 or pi, any number that is x, this is still true. If you don't believe me, try it. Plug in a few values for x, and this will always be true. So let's just plug in 1. That would be 10 minus 6 is 4, and 2 times 5 minus 3, 5 minus 3 is 2, 2 times 2 is 4. If you plug in 2, 20 minus 6 is 14, and then 2 times 10 minus 3 is 7, 2 times 7 is 14. You get the same number, no matter what you put in. So we can't write every possible value for x because it's literally every number. So for this one, when we have a true statement that we end up with after all the variables cancel, we write the solution as all real numbers. So that means x can be any real number. So it could be, again, 1, 2, negative 71.348. Doesn't matter. Every single number is a valid solution. We have a shortcut as a way to write that. We have a symbol that's like 2 vertical lines, and then we draw an R over on the right side. So it's kind of like an R, but then there's like an extra vertical piece on the left that connects across the top like that. So you can write this as the words, you can write it as the symbol, and knowing about both is important because you may see it either way. Another thing you may see is it may say x is an element of the real numbers. That just means that x is anything within the set of real numbers. We'll talk a little more about sets and set notation later, but that's a way, if you're like Googling things, that you might see it written. It means the same thing as all real numbers. So this is all saying the same thing. So those are our 2 main new topics to watch out for in algebra that you haven't seen in previous years. So we had cross multiplication, and we had special cases where all the variables cancel and we end up with no solution or all real numbers as solutions.